Swayam Prabha. Digital India. Educated India.
Welcome back. In lecture 33, we will talk about decision trees, and this is a three-part lecture. So the different concepts that we will cover in this particular lecture will be on decision tree, how decision trees are built, decision tree typology, entropy. Then we will talk about the concept of information gain ratio, and then calculation of entropy. So a decision tree is a supervised non-parametric machine learning algorithm, and this is used for mostly classification, but also could be used for regression as well. And what it does is it models decisions using a tree-like structure, as you can see in this particular images. So this tree, actually you can see that it is more like, it translates a particular choice or a result into this simple if then else rules. That means if I say that, well, if a person, suppose I want to look into the decision of modal choice, that is what most people use to undertake some trips, like for example based on a particular person's income and what kind of vehicles he owns, he actually decides which kind of vehicle he will use. So I can say that, well, I can ask a series of questions which will result in finding out the way the actual the mode that person chooses. Now, if the questions could be asked in such a way so that whenever we ask these questions, we will get the correct results, then it is like a decision tree structure. So in this particular case, you can see that the first question I'm asking is income greater than 50,000? If it is yes, then I will ask further question. If it is no, I may ask further questions. So after that, if it is yes, I'm asking another question, that is is car ownership greater than 1? Now what I find from the samples which we are dealing with is that means when both income is greater than 50,000 and car ownership is greater than 1, and if the answer is yes, of course, then the choice that person will make will be car. And in the other case, the choice that if income is greater than 50,000 but he doesn't own more than one cars, then so he says no. So in that case, the choice would be auto rickshaw. Similarly, if his income is lesser than 50,000, that is, he is saying no to greater than 50,000, and I'm asking another set of questions like, is its income even lesser than 20,000? So it is either more than 20, less than 20, or it is between 20 and 50. So if it is less than 20, then he is most likely choosing a bus. And if it is between 20 and 50, he is most likely choosing an auto rickshaw. So these questions I can ask for any individual and I can get the results of his choice. But whenever I am developing a model, of course, I have to decide which questions I should ask, and then that would give me the right results. And I have to generalize it over all the samples. That means, suppose I have a sample where I have surveyed around 50 individuals. I know what answers they have given, and I also know their income, their car ownership, and other things. In that case, I have to find out which are the right questions should I ask. In that particular context, if you see, we are starting with one question, which is income greater than 50,000. That is known as the root node. That is, we are starting here. The entire data set can be categorized from the root node. That means this question will split the data set into 2 or more parts. Now here we have split into 2 parts, but there are different sorts of decision tree algorithms that we can use. Some are designed for a binary split, that is, it splits into yes and no's. Some are designed for multi-class split, that is, it can split into all the different classes that is possible when I ask a certain question. Then whenever I'm asking, after I ask the first question, I could ask subsequent questions as well. So these are known as the decision nodes. That means at every stage I'm taking a decision and accordingly I'm moving forward. So these are known as decision rules and then decision nodes, and whenever we are arriving at the final result, that means we cannot split or we cannot create further branches, then it is known as the leaf node. That is the final prediction, which is either a class or a particular value. So of course, if it is a regression task, then it would be a value. If it's a classification task, it would be a class. So each question is a decision node, each answer a branch, and the final choice is a leaf node. So obviously the first question that I ask is also known as the root node. So at each decision node, a decision tree splits the data into subsets based on the value of input features, thereby constructing a predictive model through successive splits. That means we are dividing the data again and again into smaller and smaller subsets, and eventually we are resulting to the final result or whatever is the final outcome of this particular classification task. So decision trees, why we use them? We earlier learnt linear regression. We have learnt other sorts of ways to look into classifying data. Now these decision trees can model or handle non-linear relationships. That is, when the decision boundaries are non-linear, that means in that case I will go for a decision tree. So it's also, decision trees are very easy to build, also they're easy to interpret and visualize. Why? Because we can see a tree like structure which help us to visualize, and we also know that what are the if then else rules, which are the questions that I need to ask. So it's also very easy to interpret as well. And it also doesn't require any sort of feature scaling. That means I don't need to normalize the data. That means using encoders, we usually sometimes in machine learning we have to convert, or in any kind of model building, we convert categorical variables into dummy variables, or numerical variables we need to scale them. So in this case, numerical variables, even though they are not scaled, doesn't matter. It is still, it doesn't create much problem. So it can also work with mixed data, both numerical as well as categorical. Now problem is, I can keep on asking questions, and the more I ask questions, more would be the number of branches, and eventually I will arrive at the final result. So decision trees are always prone to overfitting. That means the more questions I ask, the questions will result in an outcome which would actually match the final outcome, but it would match this data set, but it may not match other data set because I'm asking too many questions. So these decision trees are prone to overfitting, instability due to data sensitivity, and bias towards features with many categories. So usually we end up asking questions about those features which have got many categories. Those becomes more important. So these are some of the problems with decision trees, but there are some solutions to it as well. So we use something called pruning here. So these pruning techniques actually help us to decide that how much I should build the tree. That means how much branching we should allow, or at what stage I should stop the branching. So that means if I am doing branching which are only giving me minor gains, in that case there will be no use of doing that kind of branching. And the other way to avoid this problem is to go for ensemble methods. That means instead of using simple decision trees, we can go like create different ways, like we can create many decision trees, or we can use techniques such as boosting to actually increase the chances or increase the more to generalize the results of this particular model. So that means this ensemble techniques is a combination of different approaches using decision trees, of course, so that their accuracy actually improves. Decision trees are broadly classified into two types based on the nature of the target variable. So one is of course known as classification tree, where the output is categorical in nature. So every leaf node stores the final class level or the class probability. Whereas for regression decision trees, it is for continuous outputs, that means which are continuous variables, and leaf node in this case will store the mean value of the final output at the leaf node. That means suppose there are 4 samples remaining at the leaf node, we take the median value and that would be the result shown here. So the next question comes is how decision trees are built. That means now that I know that I have a set of data, I can ask questions to arrive at the final outcomes. Then what are the questions should I ask, right? What is the splitting criteria? So the algorithm splits the data at each node. It could be root node or a decision node based on the feature that results in the best separation of data downstream. That means from at this point, whatever is the data remaining, I will choose the feature which will result in the best separation of data into two different distinct groups or multiple groups depending on what kind, what are the number of classes. So first job is to determine which feature we should use as the root value, and not only that, after the root value, even in each stages what would be the features we would use. So in classification, the algorithm chooses the feature that most reduces uncertainty or entropy. So this is a very, very important concept. That means uncertainty or entropy, we will discuss that in detail. What it means is we will choose a feature where after asking, using that feature to ask questions, we will result in more distinct splits. That means there will be less uncertainty. And in regression, of course, here we have got continuous variable. It chooses the feature that best reduces variance or mean squared errors. So that means root mean squared errors or mean squared error, right? So it reduces the variance. That means before the split, what was the mean squared error? After the split, when I have divided the data into two groups, what would be the mean squared error of these two separate groups, and then we can add them up. So in classification problems, the way we go ahead is we use two measures. One could be an entropy based measure, or it could be based on Gini impurity. And within entropy based measure, we will study entropy, and then there are two distinct measures are to measure the information gain or the gain ratio. So this is how we will distinguish that, okay, which are the features which are showing us better results. And in case of regression, we will use variance reduction or mean squared error. So these are the two distinct approaches that we will take in either classification or regression tasks to determine which features are more important in the sequence of decisions that I will or sequence of questions that I will ask. So information gain and gain ratio, it is basically it is the reduction in entropy after a split. So what is entropy? Entropy is uncertainty. So after a split, if the uncertainty reduces, that is actually desired. And gain ratio is basically a version of it where it is a normalized information gain, which is used in one of the algorithms known as C4.5 to reduce bias towards high cardinality features. That means in case I have got high cardinality features such as multiple classes are there for every feature, so that means that would have an effect. So to normalize, because then those would be chosen faster. So then to normalize that effect, I will go for this gain ratio instead of pure information gain. So the other question is, how long should I build? That is, what should be the stopping criteria? How long we should keep on dividing the tree? So the tree building process stops when certain conditions are met. Either it could be the maximum depth reached, or minimum samples per leaf achieved, or no significant reduction in impurity. So most important is of course this one, which is no significant reduction in impurity. But also we can set the other two criteria as well. Now what it does, this entire process, what it does is, starting from the root node, the model evaluates the relevant feature of a data point and follows the corresponding branch based on the features value. So we will first start with the root node, then based on the split I will come to the next point, then we will keep on moving like that. And then this process continues recursively until a leaf node is reached. That means we cannot further divide the data, or rather we have already we see that the data, there is not too much uncertainty left. So sometimes we have to do pruning, that is we do not want to have the problem of overfitting. So to prevent that, we go for pruning. That means if I keep on asking question, dividing the data, of course, the results would, we will come to a point where we will come to, the outcome. That is, it will be like there is no other option than to consider it as a leaf node. But the problem is, if I keep on, increasing these branches and all, then there is chances of overfitting. So that we have to prevent. So to prevent a tree from growing too complex, pruning is actually utilized. So it helps in generalization. So this involves cutting branches that do not provide significant improvement in prediction accuracy. That means even though I am dividing it, it is not actually giving me more, information gain or, gene impurity, whatever I am choosing as a criteria. So once there are different ways we can do that. There is pre-pruning, that is, following a termination rule, we stop the tree until a certain limit. Post-pruning, we first grow the full tree and then we see which are the branches which are weak, that is, which is not resulting in more, information gain or reduction of, this uncertainty. Then we will remove them. And then there is pessimistic pruning, where we iteratively remove, some rules, that is, some of the subtrees which has got the list error. That means those are ones which will have not, that doesn't reduce much of the error. We will remove them, but we take out one and then we, run the model and then we take out some other. So we do multiple iterations of this and see which one works better. That means after taking one tree, which one would give the better result, and accordingly we proceed. So in pessimistic pruning, a sequence of trees is generated by iteratively removing decision rules. A subtree is pruned if replacing it with a leaf does not increase the pessimistically estimated classifying error. And this process continues until no further pruning is possible without increasing the estimated error. So this is like going backwards. So I first go to as much as possible and then I, go take backward steps to come to a point where actually by, without, if I keep on doing pruning, the errors will increase. So there are different kinds of decision trees, of course, and usually it is constructed using top-down induction algorithms, right, where the tree is built from the root and a root node and then downwards by recursively selecting the best feature to split the data at each step. So that's how we go from the top to the bottom. And then there are several algorithms that we use. The one very important algorithm is ID3, Iterative Decommodizer 3. Which was proposed by Quinlan in 1986. So this is the earliest, more or less one of the earliest decision tree algorithms, and it is mostly used for classification problems, not for regression tasks. And it selects splitting attributes based on information gain, right? And we will show you how to do that. And then it builds trees in a greedy top-down manner. Now the problem with this is it is biased towards attributes with many categories and do not support pruning. So that's one big limitation. It doesn't allow pruning and also cannot handle continuous variables. So this is another input. That means it cannot do regression and all. So in any continuous variables that is there in the data set, it will not be able to proceed further, not only for regression, for any classification task and so on. Then came the C4.5 algorithm again by Quinlan in 1993. It improves upon ID3 by introducing something called a gain ratio, which normalizes information gain, and this allowed pruning mechanisms which is required for reducing overfitting, and this can handle also continuous attributes and missing values, and then it produces more compact and generalized trees than ID3. So that means it is a more better way to develop a tree. So this, and here it has got a lot of benefits over this ID3 algorithm. Then there is another algorithm which is very, very popular, particularly in machine learning, that is CART, Classification and Regression Tree by Brayman in 1984, et al. In 1984. And this is the most widely used decision tree framework. Why it is? Because it allows both classification and regression. And it uses, instead of we can have, instead of splits into as per classes, it does binary splits. That means even though there are multiple classes, I will do binary, one and other, right? And then we will keep on other. Like initially we said income greater than 50,000, then again income greater than, lesser than 20,000. So I will gradually split the data. So I cannot do it all together. So that means we go with binary splits only, and there are only 2 child nodes. So that simplifies things. And splitting criteria over here is Gini impurity for classification and variance or MSE reduction for regression. So in 2 different cases, as per the classification or the regression task, we will choose 2 separate approaches. And it also allows us to do pruning. It includes a cost complexity pruning algorithm that automatically balances model accuracy and tree simplicity. So now coming to the concept of entropy, that is to understand how this decisions taken for feature selection. So as we have discussed, entropy measures the degree of disorder or impurity in a data set. That means more mixed the data set is, like if the probability of a binary class is, it could be from 0 to 1, that is, how likely it is. So if it is 0.5, obviously it should be 0.5. If it is 0.5, it should be like, that is everything is mixed. Yes and no's are mixed. So in this case, the entropy is, highest. That is most uncertainty is there. If it is either towards 0, that is more yeses or more lows. In that case, we can say that entropy is maximum. That is, I equal to that entropy value is 1. So that means entropy ranges from 0 to 1. Probability also ranges from 0 to 1. At at the middle part, at 0.5 probability, we have the maximum entropy. So high entropy means data is highly mixed, low entropy means data is more homogeneous, and zero entropy means data belongs to only one class. That means we would be able to categorize that. Now entropy is measured using this formula, entropy S equal to minus summation I equal to I over n pi into log to the base 2 pi. Now pi is the number of samples in class I divided by total samples. So pi is the proportion of class I in the data set. So this is a very easy way to calculate entropy. So pi is the proportion of that samples, and we multiply with its log to the base 2. So it represents how frequently a class appears in the data set. Now the term, we are taking log of pi because it measures the information content of an event, right? So this comes from information theory by Shannon, which was proposed in 1948. So the information theory tells us that if I take a log of this, this proportion, then automatically it tells us about the information content of a particular event or occurrence. Now rare events means low probability, are more surprising, and therefore carry more information, while common events carry less information. So log actually allows us or ensures probability decreases and information increases. So that's why we are taking a log. So when probability is less, information would be more. So using a base 2 logarithm measures information in bits, in yeses and nos, and it is consistent with the binary decision structure of decision trees. Now pi and log of pi are multiplied to weight the information content by how often the class occurs. So this acts as the weightage, and this gives the expected information needed to classify a data point, that is average amount of uncertainty that must be resolved to determine its class level. So basically this allows us to measure what is the uncertainty in a data set, and then we can say that when we do different splits, this will be changing, and then we can measure if information is gained or not. So over here you can see exactly that. So information gain is a key concept that is used in decision tree algorithms to decide which features should be selected for splitting a node. The feature which has which gives us more information gain, we will definitely select that. So what it does, it measures the reduction in uncertainty or entropy after splitting the data set based on a particular feature. Now that means the feature with the highest information gain is selected as a root node or a decision node as per at what level of split we are. So the formula is given like this. This information gain is S is basically the original data set of the parent node, and A are the attribute features being evaluated for splitting, like income level, car ownership, as we discussed earlier. So first we calculate the entropy of the actual data set, and then we subtract from it the summation of entropy of all after we have used a feature to divide the data into different groups, for each of this group, that is subset of data, each subset of data where attribute A takes the value V, for each subset that particular attribute will have different values. So we calculate that means, and then we calculate the entropy of that subset only, not of the entire thing, and we then multiply it with SV by S, which is the weight of the subset SV. That means how much of how many of those values are there, how many of those that proportion of data is there in that particular subset, of the proportion of the entire data is there in that particular subset. So entropy of SV is the uncertainty after splitting on attribute A for that particular group of data. So this actually means the weighted average entropy after the split, remaining uncertainty after splitting on attribute A. So this will be even further clear when we will show you an example. Now, so either we can go with information gain, or we can also go with the gain ratio as well. So this is an improvement over the IG, since IG may be biased towards attributes with many categories. So that means that, because as we discussed that initially the ID3 algorithm that was developed was based on IG, and and it was biased towards attributes with multiple categories. That is where the C4.5 algorithm came in, and now we saw that if we normalize information gain, then these problems could be taken care of. So, so this normalization of information gain is actually, we see that how evenly the data is split, and based on that we can also move forward. So split information measures how evenly the data is split irrespective of class levels to correct bias in information gain. So split info SA is equal to minus. So here again for different values of A, we see that SV by S, then I take log to the base 2, and then again on this side also there will be SV by S as well. So what it tells us is gain ratio is basically that means, and then what we can do is this gain ratio normalizes information gain using this split information data, and this gain ratio is this information gain divided by the split information. So this is how we are normalizing information gain, by dividing it by the split information that we are measuring over here. So information gain measures the reduction in entropy after a split. Split information measures how evenly the data is partitioned, right? And dividing the two reduces bias towards attributes with many categories, and gain ratio is normalized. Basically in that case we can say it is a normalized information gain. So now coming to an example which will absolutely clear what is happening in this particular case. So we have a data set over here which is a very common data set. I have just changed it a bit. What I am saying is a person decides to drive a bicycle, either given in a yeses or no's, depending on the weather, the temperature, the humidity and the wind. In certain days the weather could be sunny, overcast, rainy and so on. In temperatures could be hot, mild or cool, or humidity could be high, normal, or wind could be strong, weak and so on. So you can see that we are recording this particular information, and then we are saying that if that person is taking a bicycle for some trip. So I have a hypothesis that actually these are affecting my judgment to choose a bicycle. So obviously this is a case where we have two choices at the end, and these are the features, or rather these are the variables based on which we take a decision on the final outcome. So as for entropy calculation, entropy S, that is the entropy S of the entire data set, it is minus pi into log to the base 2 of pi, which is because there are two classes, no's and yeses. So we will do it, we are taking summation of both yeses and no's because these are the two classes right now. So 9 by 14, there are 9 yeses and 5 no's. So 9 by 14 log of 2, 9 and 9 by 14 plus 5 by 14, which is the number of no's, into log to the base 2, 5 by 14. And this total, when it calculates, it comes to 0.94. Now that we know that this is the overall entropy, now I have to choose that which where should I start asking question? Which feature is more important, right? Which feature should I start with, right? So I have got features like weather, temperature, humidity, wind, and these are the four features. So let us take the first one, that is weather. So first, this could be have three classes: sunny, overcast, rain. So that means weather could be of three kinds. Now what I do is, for each one of them, that is, if I go back, if you see this, each one of them is basically this SV. So for each one of them, I am calculating how many yeses and nos are there. For sunny, there are 2 yeses and then there are 3 nos. So for sunny, these are marked over here. You can see there are 1, 2, 3 nos and 2 yeses. So this is a sunny, this is a sunny. So these green ones are the yeses. So entropy of sunny is 2 by 5 log to the base 2 by 5 plus 3 by 5 log to the base 2 3 by 5, which comes to around 0.971. Then overcast is 4 plus 0, that is 4 are positive and 0 no's are there, right? Overcast I can see over here, this is overcast. So for all the overcasts are yes, there are no no's. And then there is rain as well, where it is 3 plus 3 and 2, that is 3 yeses and 2 no's. So here the entropy is 0.971. And because here entropy is overcast, that is, it is a pure node, that means it is 0. That means here there is no, it has got, no uncertainty. So we know exactly the result over in this case, right? If it is if a sky is overcast, definitely a person is not going to take a bicycle because he may feel there may be rain. Okay. So now after we have done that, now that we have found for entropy for each of these groups, then we are going to find this value and then we are going to add all of them up, right? So we are taking their proportion 5 by 14, that is how many values are there in sunny, then how many values are there in overcast, and then how many values are there in rain, and then multiplying with the information gain for each one of them, and I am adding them up to get the total entropy after the split has happened. So that comes to around 0.693. Now I say that information gain is the previous entropy minus after the split whatever is the entropy remaining. So that comes to around 0.2464. So this is the information gain that is happening. So similarly, if I go with humidity, wind, temperature, so this could be the other features that could become the root node. I see the information gain is for humidity comes to around 0.1516, for wind it is 0.0478, and for gain for temperature it is 0.0289, right? So of course this has got the highest information gain, so we will choose this as the root node. So that means our first question would be, what is the weather like, and based on that we will take a call. So once I do that, I split the data. So I have got either the weather is sunny or the weather is overcast and then the weather is rain. So over here I can straight away say, if it is overcast, then nobody is going to say, everybody is going to say, sorry, last time I told just the opposite. If it is overcast, everybody says yes. That means everybody would be using a bicycle because there is not that much amount of sun, and so you will not get tired, so I can use it, right? That could be the logic. Now coming to to the next steps, now that we already have a root node and then we have subsequent nodes after that, we have reached a position over here, then we can ask subsequent questions. That means we can decide that after I get a result of this particular branch, what question should I ask? What would be the next decision node? So obviously if I start with this one already has got an answer because there is already full split. That means there is no uncertainty left. But here there is uncertainty, here there is uncertainty. So how can I ask further question to reduce this uncertainty, and we'll be able to answer exactly what is the final choice. So for sunny, I will have now, these are the data which belongs to sunny. So 5 data, right? 5 rows of data. So now I can ask question about, the next question could be, if it is sunny, then what is the temperature, what is the humidity, what is the wind, and so on, right? So again, now my data has split it up, and this is a small split that we are working on. And here we have got 5 records, and the entropy of sunny is 0.971, which we measured earlier as well. So now what we can say is, for temperature, I will have, if I ask the next question is what kind of temperature. So either it could be hot, mild, or cool. So for hot, there are 0 yeses, 2 no's. For that means it is 100%, we are having a split. For mild, we are having 50-50 split, that is 1 and 1, so that is entropy is 1. And then for cool, again there is a 100% split, then automatically if you put that in the formula as well, you will get this value, and it would be 0. So now weighted entropy becomes, when I take the SB by that particular total subset 2 by 5, so 0 plus 2 by 5 1, and this comes to around 0.4, right? So similarly we can do for humidity, we can do for wind, and we can calculate that, okay, what are the weighted entropies for all this. And finally we came down to the to see where we are having the most amount of gain. So we can see that that when we are having this sunny or humidity, that is both, it is sunny as well as humidity, we are asking a question with what is the humidity now, then this is the total the information that we are gaining, where here the information gain is much less, and so further less is over here. So this becomes the decision node. So that means after I ask sunny, I will ask the question, what is the humidity, is it high or normal? So then I can get the best possible split, right? So over here the humidity, this weighted entropy is 0, so obviously if that is 0, this is the best possible split that is possible, right? So in case of wind, it is not that good, and accordingly we are getting this value. So finally we can say that when we are asking this question with humidity, we are getting either high or normal, and we are eventually all highs are no's and all normals are yes, and that means we are having a perfect categorization. And then we can also repeat the same process which we did with sunny with rain as well. And here there is again 1 2 3 4 5 data points, and then we can find the entropy of rain. And then once we have done that, we find the for taking rain as the as from the point where we start asking questions, then we find out what is the weather, temperature, humidity, wind, and so on. And when we do that, then we can also find out about the different values for that, and we will see that the gain is maximum with wind, and this is 0.971. So that, because again we see that and if when we do that, we know that if I ask the next question as wind, the result would be no and yes, which would be perfect answers, or there would be perfect classifications. So this is how we build the final decision tree. So the way we predict is, if weather is equal to overcast, then drive bicycle equal to yes, straight away. If weather equal to sunny and humidity equal to high, then also drive bicycle equal to no. If weather equal to sunny and humidity equal to normal, then drive bicycle equal to yes, and so on. So this is how we gradually build the decision tree, and that is how we can interpret the results as well. So these are some of the references what we have used. And to conclude, decision trees convert data into interpretable if-then-else rules by recursively reducing uncertainty, making them powerful and transparent models for decision making. Thank you.